a function, we start with creating the control flow graph, which describes the branches and as the edges of this graph and the straight line code as nodes. These nodes are called basic blocks. And they either have one successor, like this one, which joins after these two, they join after the if statement, or two, if there is a conditional branch, or for switches, they can have any number of successors. So when we analyze the branching structure, we are not interested in the instructions in the basic block. So we just look at this graph with nodes, and we don't care about the instructions. We add two special basic blocks called the start vertex, and I will either say vertex or node, or an exit vertex. The start vertex is actually not necessary because we can use the first basic block which we normally come to in that function. But the exit is required for practical reasons, namely that, well, first of all, there is an algorithm which analyzes control flow backwards instead, and since there can be multiple return statements, it's much more easy to have just one exit. So we can start from one particular basic block and go backwards in the control flow graph. And apart from that, return statements, they are usually collected in one basic block. To do a return, depending on which function it was, there may be just one instruction. Then there is no, if it's a void function which has not created anything that should be restored, then it's sufficient to have just one instruction, and then it can be in the basic block the return statement was in initially. But if we need several instructions to restore the stack pointer, for instance, and do various things, then it's better to save memory to put all these return statements in one basic block and have an unconditional branch to that return. So in that situation, it's better to have a special exit. Okay. So now we come to the first question, namely, what will we do with this control flow graph? Well, actually, we should also consider how can we construct it. It's very easy if we just scan all the instructions. Whenever we come to a label, then we start a new basic block. And when we come to a branch, we create an edge to that basic block. If it's to an as yet unknown basic block, well, we create that basic block anyway and put the branch there. And then we will fill it with instructions when we see the label. So this is completely trivial. What we want to do is to know if we have been in a particular node when we are in some node. So say we are in Y, can we then know that we have been in X? No, we cannot, because execution might go from S to U to V to Y. But if we are in Y, we certainly must have been in S and U before. There is a relation called dominance, and this dominance relation describes this. So we say that U dominates V if all paths from S to V include U. So S dominates all vertices, and no vertex except S itself dominates S. So why would we want to know this? For instance, if we have if we compute A times B in Y and have already computed A times B in U, then since U dominates Y, it may be useful to reduce the value instead of recomputing A times B in Y. So, dominance analysis is about finding which node dominates the other nodes. And the fastest algorithm for this was developed during several years and published. The perfect version in 1979. Many people have tried to make a faster algorithm, and all of them have failed. Of course, there can be special situations when it is possible to have a faster version, such as in codes, in languages, or in particular source code without goto statements. But with any input directed graph, this is usually the fastest algorithm.